Okay, everybody. Well, I guess, it's 11:11. Probably time to start. Make a wish, exactly. So, not too many people here, so if you have questions, we can kind of like discuss together and everything, and it's good. I'm trying on my iPad today. I don't know. I've never done this. I don't know why this notification keeps coming up, but we'll just put it away for now. So I'm still recording. I hope it's working, and if it's not, it's not. But what am I going to do? Okay, so I just have, again, the labs are always like extremely short, right? So I kind of like, it's nice to kind of put other things in there too. So we'll talk today about congruences and just, maybe we'll define it together and we'll discuss kind of how they work. We'll do the questions, which will take 5 minutes. And then I have just kind of like a more fun, kind of an activity which comes from a different kind of algebra, like a Boolean algebra kind of thing that is related to congruences. So we'll talk about that. Does anybody have any particular questions they want me to cover today? Like anything from the textbook or anything like that? No? All right. So today, let's get into it. Hopefully this works, and hopefully you see everything on my screen properly. Okay, anyway. So congruences, right? We make statements like 5 is congruent to, 2 mod 3, right? That's like a statement we would make. And what does that mean? Is this true, first of all? And then second of all, what does that mean? Yeah.
First, it's true, and second, it means that there are 2 remainders of 5 in terms of 3.
Yeah, right? So it's like we can think of the numbers, right, as, so like by definition, right? By definition, A is congruent to B mod N if, N divides B minus A, I think that's what it was. I'm right there. Yeah.
So when you say it's congruent, is it like 5 is congruent to 2, and then mod 3 is like something you have to add to the whole thing to make them congruent, or is it like 5 is congruent to 2 mod 3?
Yeah, no, it's kind of like all this is just notation. Okay, that part is just kind of notation. It goes together. One second. So when I say, if I just said 5 is congruent to 2, that wouldn't be enough information, So I have to say what the mod is, right? So another notation for this is that you could also say like 5 is congruent to 2 mod 3, right? And that would mean exactly the same thing. And that's actually kind of how I prefer to write it. Okay, because it's a little less complicated. Yeah.
Would it be B minus or A minus B?
It doesn't really matter because if n divides b minus a, then n will also divide a minus b. So this is like our definition, right, of congruence. But I don't like this definition of congruence. This is not how I think about congruence ever when I'm thinking about it. I mean, unless it's like in a particular situation. Or rather, I think of it like this, right? So, I mean, this is like a proposition maybe that you could prove. But we would say A is congruent to B mod N if and only if A is congruent to B. Let me just use the 5, 2 as an example. 5 is equal to B plus a multiple. Did I spell that right? No, I didn't. Multiple of N. Oh, not 5A, right? Right? Yeah. Right. This is, okay, so it's a proposition, meaning it's not like that's the definition of congruence, but you can prove this, that if it's congruent, then this must be true. So what do I mean by that, right? So like, let's look at our example here. This 5 is congruent to 2, right? Well, I guess I can just rewrite it. So 5 is congruent to 2 mod 3. And the reason this is in my head is because we have that 5 is equal to 2 plus 3. And what do I mean by that? just literally reading this out, when I look at this, I say 5 is 2 above a multiple of 3. That's why this is true, because 5 is 2 above a multiple of 3. So in general, if you have A is congruent to B, right, we would just say that A is B above a multiple of n. And then that's true. So that's what I mean by this, right? A is B above a multiple of n. And this is a much easier way, in my mind, to actually think about what's going on. And it is equivalent, because it's like if and only if, right? So it is an equivalent way. So like, for example, really quickly, I can say like 10 is congruent to, I don't know, let's say, let's say to what mod 3? Well, why am I using mod 3 all the time? Mod 4, well, it's congruent to 2. 10 is 2 above a multiple of 4. What are the multiples of 4? 4, 0, 4, 8. Okay, so 10 is 2 above a multiple of 4. I just think that's easier than thinking about b minus a, n divides b minus a. I mean, that doesn't really mean anything to me. Yeah?
Say that 10, so you've got, so if I increase the 2 by another 4, so 6, because 10 is congruent to 6 and 6, right?
Yeah, because it's also 6 above a multiple of 4. 10 is also 6 above a multiple.
So can I say that, so I add 4 each time, so 2 plus 4 is 6, plus 4 that's 10, and plus 4 is 14, so can I say that 10 is congruent to 14?
We probably wouldn't go bigger, but I mean, let's see why, right? So if that's true, you're saying 10 is congruent to 14 mod 4. That means that 10 is 14 above a multiple of 4. Sure. So what are the multiples of 4? Starting at negative infinity, whatever, blah, blah, blah. Negative 4, 0, 4, right? So 10 is 14 above a multiple of 4. The multiple of 4 being negative 4. So it's like, sure. You usually don't go bigger with congruences, though. It's like, to help us usually with congruences is that, like, it's technically true. But yeah, you usually want to restrict, when you do mod 4, usually the thing you're saying is congruent to is going to be between 0 and 4, or 0 and 3, I guess. I'll just repeat for you. I just say, like, that's our definition of congruence, and that's my definition of congruence, right? That's how I do it. Yeah, so that's all we're saying here. So the idea is let's investigate a little bit. I mean, I think it's good to think about let's say Z5, I don't know, right? So Z5 are the integers mod 5. That's what that represents. Like, I think about the whole list of integers, but I take each one mod 5. So let's look at our list, right? So, the regular integers here, I guess I write this as an example. The regular integers here are, let's say, like -2, oops, wrong way. Just ... -3, -2, -1, 0, 1, 2, 3, 4, 5. Maybe I won't do 5. Let's do 3. 6, 7, 8, 9, 10, ... right? So we just think about what the number is congruent to mod 3. And what I'm also going to do is I'm just going to highlight all the multiples of 3, right? So now, yeah, I'll deal with the negatives in a second, but yeah, okay, sure. So now every number is one of 3 things. We've broken every integer into one of 3 things. It's either a multiple of 3, it's 1 above a multiple of 3, or it's 2 above a multiple of 3. There are no other options. All the integers in Z3 is what I'm saying, right? When I take everything mod 3, everything's either a multiple of 3, 1 above a multiple of 3, or 2 above a multiple of 3. You can't say it's 3 above a multiple of 3, because then what is it?
0.
It's congruent to 0, but yeah, still a multiple of 3. Question, or?
Sorry, that's Z with the subscript 3. So you say you had an equation in the textbook and Z with brackets mod 3, or?
I don't know how he writes in the textbook. Does he write in the textbook like that? He says Z.
No, that's what I'm asking you. I don't know.
Oh, yeah, no. This is like standard notation. This just means take the integers and do mod 3 to all of them. See what they're congruent to mod 3. So what I mean by that, right, is that this, 0 is congruent to 0 mod 3. 1 is congruent to 1 mod 3. 2 is congruent to 2 mod 3. 3 is congruent to 0 mod 3. right? Because 3 is 0 above a multiple of 3. And so what we've done is we've basically, so I'm just going to keep going like this, right? What we've done, maybe I should actually maybe mention those steps there. Like 4 is congruent to 1, right? Because it's 1 above a multiple of 3. 5 is congruent to 2 because it's 2 above a multiple of 3. And sorry, that should not be 3, that should be 0. 6 is congruent to 0 mod 3. And what I want you to really notice is that all the integers became 0, 1, and 2. I don't have any other options now. Even going backwards, I mean, just to keep the pattern going, -1 is congruent to, well, you could say -1. It's 1 below a multiple of 3. But just to keep the pattern going here, we could say it's congruent to 2, -2 is congruent to 1, and -3 is congruent to 0 mod 3, right? Because -3 is a multiple of 3. Yeah?
So does it work either way, or does it always have to be like adding like?
No, yeah, it works either way. You could say that.
5 is 1, -1.
Yeah, right. You could say like 5 is congruent to -1 mod 3. Because 5 is 1 below a multiple of 3. That's fine. But again, when we do congruences, you could always get that number to be between 0 and -1. Just the standard form of having it, right? That's kind of like a nice way of having it there. Like I can make this number between like 0, 1, or 2. In this case, because we have 3. Yeah, question?
Sorry, so can you go back up to the,
This one?
right, so you drew an arrow down saying, so if you got -1, if you got 1, the congruent to that is,
1.
1.
Yeah.
Right, but, sorry, and then you got the congruent, then if you got the congruent of 2, you got 2 minus 2, that comes, 0, and you're saying 0 is congruent to 3?
I'm saying 0 is congruent to 0, 3 is congruent to 0, 6 is congruent to 0, 9 is congruent to 0.
So you're just taking everything and subtracting it by itself?
Not necessarily. No.
Like, when I'm talking about when you do the mod, because the way I think about it is the first definition. It's
Yeah.
So you're taking everything and subtracting it to itself down to 0.
But we're not subtracting it, but like 3. Okay, so what would it be? My claim to you is like in this step right here, let's say, right?
Right, so 4 is congruent to 1 mod.
4 is congruent to 1 mod 3, right?
4 minus 1 is a multiple.
Yeah,
Right, so
not 4 minus 4, right? But 4 minus 1 is a multiple.
minus 1, right? And you got 2 minus 2, 3 minus 0, 5 minus 2,
Yeah.
6 minus 0.
Yeah,
Right, but,
because 6 minus 0 is a multiple 3.
okay.
Yeah, please tell me any more. Anything else I can clarify? Yeah.
So these are different from like the equivalent classes like 0.
No, these are the equivalence classes. These are the equivalence classes. Yeah. So technically, if I actually write the set Z3, the set Z3 is 0, 1, 2. And it's not that there's only, well, it's kind of that there's only 3 numbers, but it's just that actually all those get mapped to the same 0, right?
Right.
And all the ones get mapped to the 1.
In the sense that the professor talked about in lecture of like 0 is even numbers and
Yeah, that's still what I mean. So, yeah, so because what am I saying here? I'm saying everything's either 0 above a multiple of 3, 1 above a multiple of 3, or 2 above a multiple of 3. Which is just the generalized case, because when it was even and odd, it's like you either are a multiple of 2 or you're 1 above a multiple of 2. But we don't say 1 above a multiple of 2, we say an odd number, right? But here we just don't have a name for that. So we just say, well, it's either 0 above a multiple of 3, 1 above a multiple of 3, or 2 above a multiple of 3. Question?
So, how was,
So technically this is the equivalence class of 0, which is not how we usually notate it, but whatever. That's
so if I asked you to put the equivalent class of 3, would you give me 0, 1, 2, or?
if I asked you for the equivalence class of 3, that would be the same as the equivalence class of 0, which is 0, 3, 6, 9, 12, and also the negatives too. Right? Because the equivalence class of 3 is going to have 0 in it, because 3 is congruent to 0 mod 3. And if they have the same thing in it, then it's the same equivalence class.
So if I give you of n is any integer, positive, negative, whatever, it's always gonna be equal to 0.
0, 1, or 2, not 0. Right? Because if I give you any integer, it's either a multiple of 3, that would be 0. That would be the equivalent class of 0. 0 above multiple. Could be 1 above a multiple of 3, in which case that would be the equivalent class 1 here.
Oh, okay, right, okay, sorry, I got something. So when I give you this, I have to specify that it's by mod 3.
Yeah, by mod 3.
It becomes 0, 1, 2.
Yeah, that's what yes.
So
Right. If I give you this and I don't get any other information, then there's no equivalence relation, right? I don't know anything. But my equivalence relation is mod 3. So if it was mod 5, then my equivalence class would be like 0, 1, 2, 3, 4. Or my equivalence class would be 1, 2, 3, 4, 5. It's the same thing because equivalence class of 5 is the same as
If
0.
I gave you mod of something, then all its equivalence class would be the same, if they all have the same mod.
Yes, if they all have the same mod, yeah. Like if they are all congruent to the same thing, mod, whatever we're talking about, then all the equivalence classes would be the same.
Thank you so much.
That'd be like the mod of 1.
Right, yeah, right. Like mod 1 doesn't really mean anything, right? 1 divides everything, so everything is congruent to everything. It's not very interesting. My real point was not really to talk about Z3 here, but my real point was to talk about that we're essentially wrapping everything into like a circle. So you can imagine I guess I am talking about Z3, but everything kind of gets wrapped into a circle, right? So like if I just start counting the integers, right? 0 is congruent to 0, 1 is congruent to 1, 2 is congruent to 2, 3 is congruent to 0, 4 is congruent to 1, 5 is congruent to 2, 6 is congruent to 0, and so on. Right? Everything kind of just gets wrapped into a clock, kind of. But a clock with only 3 hours on it. So in general, right, if you had like, we were thinking Z12, right, then Z12 would be like, right, you have like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
That was so well drawn.
Thank you. It's just a clock, right? So then we have here, like, again, all the this is just like how time works, you know. Hours are like 12-hour days are mod 12, right? So it's like, what's the time? It's 10 o'clock, right? Oh, and then next hour it's 11 o'clock, and then the next hour. Okay, with time we usually don't say noon is 0 o'clock, but military time, right? Then it's mod 24, right? Right. So anyways, you could say 0 o'clock is noon, or you could say 12 is noon. It's congruent mod 12, right? So this is like 12 o'clock, and then 13 o'clock is congruent to 1, right? And then you keep going around like that. So that's like a good way to think about congruence, because so when I say Z12, I mean like I'm taking everything mod 12, right? So now everything is lumped into 0 to 11. Every integer is congruent to some number 0 to 11. It's congruent to lots of other things too, right? But we are interested in where it's congruent to 0 to 11. And these are all like the equivalence classes or the congruency classes that we have going around like that. So hopefully that makes sense. Talking about in general, I like mentioning this stuff because I feel like it makes more sense than just the definition, but it's also weird at first, right? So we're in a sense saying that like 5 is equal to 2. It's an equivalence class, right? So we are saying they are equivalent in some way. They're equivalent when we wrap the numbers around mod 3. Right? So then they land in the same spot. It's like another example of this is like angles. All angles are mod 360, right? I can give you a 365 degree angle, but that's a 5-degree angle, right? You go all the way around, just go 5 more. Angles are all mod 360. So you've done this, I don't know, in high school you had like coterminal angles and things like this in trigonometry that landed in the same spot, and that's because they were congruent mod 360. That's why they landed in the same spot. So this is just kind of a generalized version of this, right? I still have a circle. It's like if I just take 2 numbers and they land on the same thing, then they're congruent. So also, we can also say that like 5 is congruent to 2 mod, well, that's what I already said, but 6 is congruent to 3 mod 3, right? And anything in the same class, they're congruent to each other. Yeah, let me continue this for a second, right? So let me say I have 6, and then this is 7, and this is 8, and this is 9, this is 10, and now I'll do the spiral. But we can say like these kind of things. Everything in the class is congruent, so 10 is congruent to 4 mod 3. Right, because 10 is 4 above a multiple of 3. 6 is the multiple of 3, that is 4 above. So everything in the class, they're congruent to each other. That's the point of equivalence classes, they're all congruent to each other. But nothing between the classes are congruent, right? So 5 is not congruent to 6 mod 3. Everything's mod 3 in this diagram. Here, mod 12, right? And of course you can go negative, right? Like it doesn't really, it's integers, right? So it's all the same. Divisibility still works. But I think for this course, I don't remember if he exactly said that we're going to focus on positive divisors, but it doesn't really matter. It's not that much of a difference. It's just, some of our discussion is a little easier if we just focus on positive divisors. Okay. Any question about the wheel? That's what I kind of wanted to show, the wheel. So a way to represent the integers mod n, right? You can think of them, right? So again, 360, right, is how you're used to doing that, right? You've done integers mod 360. I mean, obviously rounding angles there, but angles are really continuous, obviously. But we can lump them into 360 kind of bins. Okay, so if there's no questions, then I'll keep talking about the actual questions that we have for today, and then I have a little thing for us to do after. But I feel like, well, since we talked about Z3, okay, let's just do the little thing now, and then I'll do the questions, because the questions are very boring. Okay, let's just do them at the end.
Can we do the questions first? Because I might have to leave.
Okay, let's do the questions first. Sounds good.
Thank you.
That is a reasonable request. You have to find them. Okay, so for part A, question 1A, it's saying show 30 is congruent to 2 mod 7. Instantly, is this true? Yes or no?
Yeah.
Yes. Why is it true?
2 multiplied by 4 times 7 gives you 30. 2 added with 4 multiplied by 7.
Yeah. So in other words, 30 is 2 above a multiple of 7, right? So however you want to show that, but I think how he probably means for you to show that is that like you need to show that 7 divides 30 minus 2, right? Which, whatever is equivalent to, how should I write that? Implies, I guess. 7 divides 28, which is true. How do we show 7 divides 28? Yeah, right. So the reason is because 28 equals 4 times 7. That's all. That's how we show that 7 divides 28, right? We find its divisor. Like it's like the pair. That's all. So this is true, therefore this is true, therefore this is true, therefore this is true. Yes?
So I have had trouble with this on tests because like often the equations are just like equals and then on the next line it's equals and then on the next line it's equals. But for this, should we just use like the arrows that are like?
Yeah, I can't say equals. Why can I not use equals?
Because it's not the same exact thing. It's not equivalent. It's just related.
Well, actually, I do mean they are equivalent by this double arrow, right? That means if this is true, then this is true, right? If and only if, kind of both ways there. The point is like, what does equals mean? If I say this equals this, yeah.
That directly translates to that.
That's what I mean here too. I mean, this directly translates to that. That means they do the same thing, yeah.
Equal sign is related to expressions that are some equivalent. These are relations.
Yeah, almost there. The point is that an equal sign is for numbers. That's not a number. 7 divides 28 is not a number. That's just a statement. I'm just saying something. I'm saying 7 divides 28. So I can't say 7 divides 28 is equal to 28 equals 4 times 7. I use equal sign here because those are numbers, right? Which is what you're saying. So like a number, also an expression to represent a number. This isn't even an expression to represent a number. I'm just saying something. I'm just saying 7 divides 28. That can't possibly be equal to something. Now, of course, you have to get a little into how do we know numbers are equal and blah, 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 blah. But the point is, like, an equal sign is for numbers. And for a statement, yeah, like you would usually use like an implication, but these are double implications because these are like actually equivalent. This is like, I'm just using the definition essentially. Well, this I'm using like, I'm just using the fact that 30 minus 2 is 28, but I still can't say equal because that's not it. The whole thing, where am I? That whole thing is not a number. That whole thing is not a number, so I can't say they're equal. Is that okay? Does that answer your question? Right? So it's just, yeah. So otherwise, like use just like implication arrows. And sometimes they're double arrows. It doesn't really matter, in this case it does. Yeah.
So he made a point to say that the triple line in this context is not a logical equivalence.
Yeah, it's not a logical equivalence.
So like, what is it?
It just means congruent, right? We're using this triple equal sign to mean that 30 is congruent to 2, right? That's all we're saying. It is a form of equivalence, but it's not like logical equivalence, like what we used in 110, right? Like the triple equal sign with the statements and blah, 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 blah. It is like an overloaded symbol. It has more meaning than one, right? But that's okay. That happens all the time. Okay, that one wasn't too hard. Now for part B, show 2x is congruent to 7 mod 4 has no solutions. Right, so there is no number, integer, presumably x, that I can sub in there to get whose double is congruent to congruent to 7 mod 4. There's no number whose double is congruent to 7 mod 4. And like the first one maybe is kind of weird, but oh yeah, question. Sorry, I didn't see you first.
I was just gonna say like
What? Yeah, like you had the answer, like how it is. Yeah. Okay, sure, go for it.
because any even number, which would be multiple of 4, minus an odd number is going to be an odd number.
Yeah.
And any number multiplied by an even number 2 would be
Yeah.
an even number.
Right.
So it's saying,
Right. Exactly. So being 7 above a multiple of 4 means that you must be odd, right? That's the only way to be 7 above a multiple of 4, because multiple of 4 is even and 7 is odd, so you get an odd number. But 2x is never odd, right? Okay, so that is right. Michael, did you have a question too, or
Yeah.
the same thing? Okay, so like formally here, we would just say that this is true if and only if 4 divides 2x minus 7, which is true if and only if 2x minus 7 equals 4k, right? For some k in z. Is that clear so far? Right, I'm not really doing anything crazy. I'm just saying that is the same as that. Like that just means that, and that just means that. So we're still with the original statement. I'm still just saying that 2k minus 7 must be a multiple of 4. Must be a multiple of 4. That's what that 4k means, right? A multiple of 4 for some integer. Okay? Okay, and so now we want to find some kind of contradiction or something like that, which would tell us that there is no x, right? So where do I go from here? Yeah?
Basically reiterates what he said. Therefore, an odd number, a number divided by an even number cannot give an odd number.
Sure, but is that what we see here? What is it? Is this even this odd or what? Like what is it? So is this even?
Yes, that's even.
What is this? Is this even or odd?
That's odd.
Why is that odd?
Because it's a difference of one number.
Yeah, sure, an even minus odd. You could say that, I guess, right? But I guess more, explicitly, you could just say that, well.
An even number that has a difference of a number.
But remember, what is an odd number? Like, how do we define an odd number?
2 plus 1 or minus 1.
It's two, did you say?
One above an even number.
One above an even number. So I have to write this as one above an even number, right? So I could say this is 2x, there's my even number. What is this? It's going to be like a plus 1 minus 8, I guess, right? Yeah, and then this is 4k. Let me write that the other way around. Minus 8 plus 1. And then I can factor the 2 out, right? And that is definitely now, and I guess I'll also write this. This is 2 times 2k. So very precisely, that is an odd number, and that is an even number, exactly matching the forms, right? I know it's a little weird, that step, right? But I have to get a plus 1 at the end for it to be odd. It has to be an even number. X is an integer, right? So we know that we know x minus 4 is an integer. And so 2 times x minus 4 is even, plus 1 is odd, and then the other one is even, right? Therefore, no such solution. Any questions about this? So, like, yeah, you said it right at the start. I mean, that's the reason, right? It's like because you can't have an odd number equal to even number. But it's easy to say that, but verifying it with the algebra and the details and everything like this is the like rigorous part, right? Is the part of like we're actually proving something. So yeah. Anyways, that's that. Okay, let's move on to the next one. Unless anybody has any questions. Question 2. Show, part A, 17 is congruent to 3 mod 14. Yeah. So however you want to do this, right? You can say that this is true if and only if
17 minus 3 is divisible by 14.
yeah, 14 divides 17 minus 3, which is only true if 14 divides 14, which is true, right? So that's true. I mean, yeah, well, like you can prove this as well. Like why is that true? Because 14 is 1 times 14, right? But I think you can take it as a it has been shown that n divides n always. So then that's true, then that's true. Then the next one is part B, show 16 is congruent to 3 mod 13. I told you these questions were not very interesting, so, don't blame me. Anyone want to just talk me through it? What do I write down?
Same logic as the first.
Yeah, so tell me what to write.
14 divides.
I will throw it out that one.
Oh, wait, not 14. 13.
13 divides
16 minus 3.
16 minus 3, which is if and only if 13 divides 13, which again we can just take as a fact. True. Okay, and then part C. Part C is show 4x is congruent to 3 mod 6. Has no solutions.
Same logic as the second question.
Yeah, so someone want to talk me through it? Yeah?
4, 3, this 4x.
So 6 divides 4x minus 3. Yeah, that's...
Yeah, which is impossible because, wait, sorry, I was about to say because that can't, well, yeah, never mind, yeah, sure. Because that is an odd number, and if you were to expand, well, yeah, you can expand, that would be 4x minus 4 plus 1. 6 divides 4x minus 4 plus 1.
Yeah.
And that would be 2 times 3. Perfectly divides 2
So what's your claim at the end? What's your claim? Like, I think the final thing you're going to say is that like an even number can't divide an odd number or something like that, right? So then you'd have to prove that. We never proved that, right? That an even number can't divide an odd number, right?
Yeah, I was getting to that.
Right.
I was going to say that we should break apart the 6 and the 4x minus 3. So you break the 4x minus 3 into two brackets.
Yeah.
2x.
But remember, like, so I agree with you. It just we're gonna say here that 4x minus 3 equals 6k, right? For some k, and then now it's exactly what you're saying, right? So what's the left side gonna be?
2x, 2 whole bracket. Well, I'm skipping the steps. Plus 4 minus plus 4.
Yeah.
So 2x. No, 2x.
Yeah, 2x. You're right.
2x minus 2.
Minus 2 plus 1 equals 2 times 3k, which again, blah, 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 odd number can't equal even number, you're done. Yeah.
Does it always have to be 2 to show that it's even?
Yeah, right. Because the definition of an even number is 2 times the number, and the definition of an odd number is 2 times something plus 1. Question over here? No? You have a question? Again, odd can't equal even. Okay, and then the very last question, and then I have my thing to do. I still want to show you something. But the very last question is 6x is congruent to 1 mod 4, show has no solutions. Solutions. Somebody else want to talk me through it? Sure.
Right, so 6x minus 1 has to equal 4k.
Yeah, right, exactly. So 4 divides that. So if and only if 6x minus 1 equals 4k, for some k in z. And now,
Can't you just go straight from can't you obviously do this odd even from here?
you can, yes,
6
why?
Minus 1, right? Sorry, 6x
Right.
minus 1.
Like, and so that's odd y.
It's odd y because you're subtracting 1 to an already even thing, which is 6 times x.
Yeah, so then your claim is that odd numbers can also be represented as an even number minus 1, which is obviously true, but like just the definition of odd is plus 1 usually, right? So
Can't I just say minus 1?
Yeah, plus
then you'd have to say claim. An even number minus 1 is odd. Okay, you prove that claim separately, right? It just depends on how you define it. If you define even numbers as 2x minus 1, then that's it. Then you're done.
2 plus 1 minus 2.
Yeah, right. So you could say that like 6x minus 2 plus 1 equals 2 times 2k. And so then you have 2, 3x minus 1 plus 1 equals 2 times 2k, blah, 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 blah. It's the same.
I mean, also this might just be a throwaway logic. Couldn't you just go 6x plus 0 minus 1 and then just do that as well?
But then you still have a minus 1 at the end, right? And again, that's the problem is like, just how did we define odd numbers? Did we define odd numbers as 2k plus 1 or 2k minus 1? Right, so obviously those are equivalent, right? Those equivalence classes would be the same, but that would be like, you show that, right? You'd show that those are the same. Yeah. And it's like, you can, like, it's just like, yeah, this is odd. Why is it odd? Because you can do this. That's why it's odd. Because that's the definition of odd, right? So, yeah, it's not really saving you too much work by doing it the other way. Is that okay? We did that 3 times, so not too complicated, and it's the same trick every time. Okay, so let me, we're almost done. We only have 10 minutes left. This is not going to take 10 minutes, so let me just, talk for a second here. There is a common misconception that when I do x plus y squared, that this is x squared plus y squared, right? There's a whole Wikipedia page about this called the Freshman's Dream or something like that. And it's like, it'd really be nice if that were true, right? But it's not. What am I missing? Yeah? yeah, I'm missing like a 2xy. That usually goes in the middle, but whatever, right? So I have this kind of additional term which makes it not true. And whatever, you know, that comes from just like foiling. I'm sure you know this. Okay, but now we can ask, okay, so this is true. This statement right here is true for what kind of numbers? Like what numbers what numbers did you know? Yeah. Real numbers, yeah, real numbers. Right? So and then everything else is kind of a subset of that we talk about, right? So we have that it's true for the rationals as well. It's true for integers. But I'm going to show you a special kind of number that this is true for. That it actually, the formula is this for a special kind of number. And that number, I mean, so the numbers that we're going to talk about are Z2. Okay, so that's the integers mod 2, which means it's just the numbers 0 and 1. Everything gets kind of jumped down to 0 and 1. And we define addition, we only have two things, right? So I'm just going to say that, I'm just going to define it like this, right? So addition, 0, 1, 0, 1, 0 plus 0 is 0, 1, 1, 0. That's like, I'm telling you this is how it works. This is not a theorem, this is a definition. That's what the addition means is that 1 plus 1 is going to go back to 0. This is essentially the congruence class's mod 2, right?
I have a question.
Yeah.
Even if you put 1 into that, that's got to be 2 on the right-hand side. No, sorry.
Well, but we're doing everything mod 2, right? We're doing everything mod 2. So that's important to remember. And then multiplication, right? We have, again, 0, 1, 0, 1, right? And then 0 times 0 is 0. This is, of course, 0, and this is going to be 1 like that. Okay, so now let's try to expand, you know, x plus y squared in this modular arithmetic, right? So, yeah, like you just regularly expanded, you're going to get the same kind of thing, 2xy plus plus y squared. But everything is mod 2. Everything is mod 2. That's what Z2 means. We're taking all our integers. So we're going to take this, right? This is congruent to what? Mod 2. Okay, well, this depends on x and y, right? Depends on what x and y are, right? So if x is 0, then 0 squared is still 0. Oh, and sorry, to be clear, you can do each term mod 2. So just you can break it up into what's x squared mod 2, what's 2xy mod 2, and what's y squared mod 2. Take care. So I don't know anything about x, so all I can say about x squared is that mod 2 it is x squared. Right? There's nothing else for me to say. Maybe I'll say this is like congruent mod 2 to x squared. This is also, for the same reasoning, congruent mod 2 to y squared. But what is that congruent to, mod 2? 0. It got a 0. Why a 0?
Because it's always multiplied by 2.
Yeah.
2 mod 2 is 0.
Yeah, right? Exactly. So the point is that is always a multiple of 2, right? 2 times nothing. So in this algebra, using this set of numbers, 0 and 1, we see that is just congruent to 0. And so it turns out that in Z2, x plus y squared is equal to x squared plus y squared, because that 2xy term is always congruent to 0. So, you know, like the dream of everybody doing algebra is true in Z2, because we get that the extra term that's left there is congruent to 0, and this is generally true as well. Like if I just have like x plus y to the 3. In Z3, we have x cubed plus 3x squared y plus 3xy squared plus y cubed. And congruent mod 3, these terms also go away, mod 3. And you just get x cubed plus y cubed if you're in Z3, right? In Z3. My point is basically that there are, you usually talk about integers. Well, I mean, the congruent to 0 is what I mean there, right? usually talk about integers, and you have real numbers and things like this, where you have these algebraic rules that work in certain ways. But now that we're introducing modular arithmetic, we can look at these more interesting sets, like Z3 and Z2, which have less elements. They're finite sets, right? They only have, like, Z3 is 0, 1, 2. But we get weird results, right? Like in Z2, you know, that freshman's dream, whatever it's called, is actually true, and also in higher cases. So this is like a little touch of abstract algebra. So if you're interested, right, you can look more into that, or you can ask me about it. In abstract algebra, you study more abstract sets and think about the algebra on those sets. That's kind of what it is. You're abstracting away algebra from what we already know. That's my spiel. That's all. So yeah, that's all the questions we have for today, and we're on time, right? It's 11:57. Yeah, sounds good. Anybody have any questions for me? No? Sounds good. I hope